Speaker is here, I suppose.
Yeah, I'm here.
Okay, now we can start.
Okay, I have opened my whiteboard, so you should see a blank white screen, right? Now.
Yeah.
Okay, so first of all, this morning I have learned that today is International Science Day, and it's my pleasure to congratulate all of you on this occasion.
Thanks.
Thank you very much.
Okay, today I will give a talk based on my joint ongoing project with Ilya Molchanov from Switzerland, from Bern. And it is based on several recent results and models, which I'm now going to present as a motivation and preparation before presenting my main results. So I will start with a model which I call random samples on a semisphere. Okay, this is model 1. And this is a model of random samples on a half sphere. Okay, so how this model looks like. Let SD plus be a d-dimensional upper half sphere. So this is an object in space RD plus 1, satisfying equals 1 and x0 is non-negative. So in a three-dimensional space, this is just upper half sphere. Okay, now let's take an independent sample from the uniform distribution on this half sphere. So this is sample from the uniform distribution on SP plus. And now let me define a so-called spherical convex hull of this sample. And this is defined as, it can be defined in several ways. So let me define it first in this way. So what is Cn? Cn is a positive hull of the sample, which is the set of all linear combinations with positive coefficients. 1 to n, alpha, I are positive. So let's make a picture. So we have a sample, say, 3 points on a upper half sphere. We have origin. Let's draw half lines or rays through the origin and these points. Let's put it here, say. And so Cn is an infinite cone bounded by these rays. So these rays are edges of the cone. And Cn intersected with SD plus is a part of an upper half sphere inside this cone. So this is a spherical triangle. Okay, let me immediately give you an alternative definition, which will be important for what follows. So alternatively, S conv can be defined of U1. Yeah, of course, this is S conv spherical convex hull of U1 UN. So S conv of U1 UN can be also written as follows. This is intersection of the images of this upper half sphere for all possible rotations in RD such that image of the rotated upper half sphere contains the sample. Okay, here SOD is a special orthogonal group. Special orthogonal group. Orthogonal group. Or in simple words, just rotations or rotations in RD or orthogonal matrices with eigenvalues being either complex or one, so without minus ones.
Mhm.
So you can imagine how it looks like. So you take a half sphere, you take independent sample on this half sphere, and then you are rotating this half sphere such that image contains the sample. And now you take intersection of all these rotated half spheres. And this will be the spherical half. So in particular, all this in 3 dimensions, these lines are arcs of a great spheres. And more general, these are also arcs of a great circles in d-dimensional space. Okay, so
Alexander, can I ask you?
yeah.
In usual linear space, we have a good representation of the convex hull as a set of all linear combinations with positive coefficients where sum is equal to 1. Is it possible to introduce some kind of aging of points on the sphere in such a way that we can also remove this definition to your case?
So in some sense, yes, because these are geodesics on a sphere, right? Our edges of this spherical convex hull are just geodesics. Mm-hmm. So we take, in some sense, extreme points of our sample and connect them by geodesics on an upper hull sphere, on a sphere, actually. Mm-hmm. And this convex hull, so the boundary of the topological boundary of this convex hull, relative boundary, of course, relative to the topology of a hull sphere, is consists of a finite number of geodesics.
Okay.
Okay, so what is the result I would like to mention about this model? So, in a recent work by Barani, Hook, and Reitzner, these are known specialists in stochastic geometry. Reitzner, 2017. They have proved that expected number of d-dimensional faces of Cn. Okay, let me write it in this way. This d-1 probably S conv U1 UN converges. So this is just a sequence of what? Of real numbers. This converges to the constant, finite constant, as the size of a sample tends to infinity, of this form. Here, kappa of d is the usual notation for the volume of a d-dimensional ball. This is a volume of a d-dimensional ball. Unit ball. Unit ball.
What is function f? Could you please?
What is f? So the simplest way to explain this is, so we can identify spherical convex hull with a cone, yeah, with this Cn. This cone is a d plus 1 dimensional object, so it has, say, d-dimensional faces in the usual sense. So, for example, here there are 3 faces, infinite faces. This one, and the third one, this one. So these are 2-dimensional faces of the cone. And these 2-dimensional faces corresponds to 1-dimensional faces of the spherical convex hull. This one, and this one. And this is what I denote fd minus 1. So in d equals 3, if d equals 3, then this is just the number of edges of the spherical convex hull, or equivalently the number of faces of the cone Cn. Okay, so surprising. So this is quite surprising result that this function.
So Sasha, but still I didn't get what is FD? Could you please repeat once again? What is FD?
Okay, let me write it in this way. FD minus 1s conv of the sample is the same as FD of the cone. And this is the number of d-dimensional faces of Cn. So this cone this is a polytopic cone in space of dimension d+1. So it has some side faces, right? It's infinite cone, so it has side faces, which are, and we count, FD is just the number of these faces. So equivalently, this is a pyramid, so infinite pyramid. So you have some apex, and you have finite number of rays from this apex, and this generates an infinite pyramid or cone. It's called cone in geometry. And we just count this number of faces. This is one face, this is second face, first face, second face, third face, and fourth face. Is it now clear?
Yeah, thanks.
Yes, but result is really strange because n tends to infinity and the number of faces does not converge to infinity.
Exactly. And
But only expectation, as I understand.
And that's what I'm going to explain in a moment. So this was a result by Marynych, Hug, and Reitzner, that expected number converts to a finite constant, and even a more recent result by Kabluchko, myself, Christoph Tele, and Daniel Temesvari. We have proved much more. We have proved, so this is a result from 2019, that I will explain the notation in a moment. PD1, Sn goes to infinity in distribution. So what notation we have used here? So first of all, PD1 is a Poisson point process on Rd with intensity given by some constant. I don't want to give it explicitly. This kind of, so this formula gives intensity of our Poisson point process. Now, this function is integrable outside every ball encircling the origin for every epsilon. So you can easily check that this function is integrable in the vicinity of infinity. What does this mean? This means that probably it's better. I can show you a picture. I can show you a picture from the paper. It's even better. Okay, can you see these two pictures?
Yes.
Okay, so these are simulations of this Poisson point process with intensity of the form I have written in dimension 2 and dimension 3. So we know that intensity is integrable in a vicinity of infinity, and this means that a convex hull of this infinite set of points, infinite set of atoms of this Poisson point process is a polytope. And you can see this on these two pictures. This is a polytope in R2 as well as a polygon, say, in R2 and a polytope in R3. So majority of points concentrate around the origin, in a small ball around the origin. And only finite numbers fall outside this ball, and they extremes generate this convex hull. Okay, so now let's go back to the whiteboard. Okay, so as I explained, this is the polytope. This is a polytope, convex hull of this Poisson point process. And vector f is a so-called f vector of a polytope. So its first component is the number of vertices. Its second component is the number of edges. Its third component is the number of what? Two-dimensional faces, and so on, up to d-1 dimensional faces. So this is a d-dimensional vector. D-dimensional vector. Whose components are number of faces of a polytope. And similarly, this quantity is the number of faces, is an f vector of spherical convex hull, which can be defined as f vector of a cone, of a polytopic cone itself, right? So we stipulate just by definition that this is shifted by one f vector of cone Cn. Why shifted by one? Because as I explained to you, say this one-dimensional edge corresponds to a two-dimensional face of a cone. So all components are shifted by one in Cn. Okay, so this is a result, and of course, this constant is nothing else but expectation of the first component of this vector. And explanation for this result is quite easy. So this is not an exact proof, but just explanation. Okay, so let's draw a picture. This is an upper half sphere. This is a north pole of this half sphere. This is a tangent hyperplane at the north pole. So we have a sample. We have origin, and okay, this is not a good point for the picture. And we project our sample onto this tangent hyperplane. So this point is so the hyperplane is a plane in RD, And by direct calculations, you can find a density of the distribution of the projected point. And it turns out that this density has tail which is regularly varying at infinity with index 1. And from the general theory, we know that as a point process, this sample after renormalization converges to a Poisson point process. And it can be checked that this Poisson point process has a density which I have written. And normalization is very simple. So the result looks like as follows. Let Tn be the linear transformation which sends d-dimensional point to a d-dimensional point of this form. Now let's take our cone. Let's apply this transformation. So this is a scaling along the first coordinate. Now let's take intersection of this with H1. This is our plane H1, say. And then this shifted in such a way that it passes through the origin. So this converges in the Hausdorff distance to the convex hull of PD1. And then, so it can be checked that f vector is continuous with respect to this convergence, and that f vector of this object is the same as the f vector of our spherical convex hull. So you can imagine easily how this picture looks like when passing to the limit. So you scale, you multiply by n along this vertical axis. So your cone Cn, which was close to the half space, becomes more narrow in this direction. And it turns out that in the limit, it is non-degenerate. Yeah, and the limiting cone can be described in a simple way. So the limiting cone is just a cone whose intersection with H1 is given by this convex hull. And this convex hull is a polytope. So this is a very simple explanation, not a very simple, but a quite simple explanation of this result by Kavluchko, Teletin, Esfrar, and myself, and as a consequence of this result by Baraniak, Hook, and Reisner. Okay, this is quite a nice result, but we can have another model which possesses a kind of similar phenomenon. Okay, what is model 2? Model 2. In this model, let's consider first a two-dimensional case. So let B2 at 0 be the unit ball on a plane. So unit ball in R2. Now, again, we have take uniform sample. And now this uniform sample is a sample from the uniform distribution on this unit disk. Okay, now let me define the so-called ball hull of the sample as an intersection. This is intersection of all translates of the unit of our unit ball, which contain the sample. So in other words, ball hull, which I will denote by PH with index B20 of a sample U1, UN, is an intersection of all translates of our unit ball. Why do I write 2 here? I don't know. It's 1 everywhere. 2 probably means stands for dimension and should be put here. Okay, so this ball is translated, so it's not centered in the origin anymore. So it's centered at some x, and intersection is taken over all x's such that B1 to x contains whole sample. Contains the sample. So let's take a look on this picture. Imagine that you are moving this ball in all possible directions in such a way that translated ball contains a sample. So what will you get as an intersection? You will get something like this. And this object is called ball hull. And of course, with this representation and this representation, we see that 2 models possess a kind of similarity, right? So we have some say bounded manifold in a finite dimensional space. We have a group. So here in the first model, this is a group of rotation, and in the second model, this is a group of translations. We have a sample from the points in this manifold, and we define hull, a generalized hull, in the same way. So we take all translations, or rotations, or images of our initial manifold under group, right? Such that image contains a sample uniform distribution. So in this way, these two models are similar, right? Okay, and what can we say about this model? It possesses a very similar phenomenon. So this is a result by 3 Hungarian mathematicians from 2014. And they say that number of, so far we have considered only two-dimensional case, and we can easily define number of what is vertex, right, for this model, and F0 is the number of vertex of this ball hull. These are the number of vertices, number of vertices. And of course, in two-dimensional space, this is the same as the number of edges, right? So of this ball hull, so this is 1, 2, 1, 2, 0 of this sample. This converges as n goes to infinity, again to a finite constant, which they calculated, and it turns out that this constant is p squared over 2. P squared over 2. And recently, so this is a preprint still not published, and moreover, this preprint still contains some errors, so they're not corrected, but the result is correct, what is it that I'm now going to present. This result is a generalization to a d-dimensional case. Ball hull. So of course, this can be all this can be generalized to a d-dimensional case. So we take a d-dimensional ball, uniform sample from d-dimensional ball, intersection of one translates of this unit ball which contains a sample. We, in some way, I will explain in a moment how we define facets, faces of full dimension for this object, and fd minus 1. This is the number of these faces of full dimension. So of the ball hull, now I put here d, put here 1, 0. And this converges also to a finite constant, which is identified in this way. Okay, so for the first time, a face of a full dimension was defined in this paper. So it's very recent work, so far it has not been defined before. And how is it defined? So take this ball hull. Its topological boundary consists of a finite number of parts of a unit sphere, right? Mm-hmm. And they are called supporting spheres. These parts are called supporting spheres. So if intersection of the topological boundary of this ball hull, if intersection of this boundary with some sphere is non-empty, then this intersection is called a face. If this intersection has a positive surface area, then it is called a facet or a face of a full dimension. Okay. And now I'm going to present new results. So as I told you, this result, even for expectations, is very recent. It's still not published. It's a preprint by Fodor. And now I'm going to explain you our findings with Ilya. So let me explain first what is a candidate for the limiting object. What do I mean by this? Okay, in this result, we had convergence of expectations, and we were lucky to find a limiting object, a limiting random object, such that this expectation is an expectation of an appropriate function of this object. So, and there is a convergence of objects themselves, right? Explained by this relation. By this relation. So we have convergences of normalized spherical polytopes. The same phenomenon occurs here, also here. So whenever, probably whenever is a strong word, but when you see such kind of convergence, it's natural to expect there should be some convergence, underlying convergence of the random objects, such that with limit constants are expectations of function, of course, the corresponding functionals of this random limit object. And now, how can we guess a candidate for this limiting object? Okay, so there are several works. So first one is by Renier and Solanke, 1972. This is a case when dimension D is larger than 2. And work by Kabluchka, also a very recent paper. This is the result about the full F vector. Yeah, I forgot to say this is D larger than 2 and result on F0. F0, but of what? So, and Kabluchko is also D larger than 2. F0 of what? By ZG, I denote zero cell of an isotropic Poisson hyperplane tessellation. Hyperplane tessellation sounds terrible, but it's quite a simple object. Poisson hyperplane tessellation. This turns out to be a polytope. And by these two references, I meant the results on a F vector of this polytope. So the number of vertices in arbitrary dimension of this polytope was found by Renier and Solanke, and Zahar Kabluchka has found the full F vector of this polytope. So what is zero cell of an isotropic Poisson hyperplane tessellation? So by this notation, for me, this is a set of all hyperplanes. All hyperplanes in RD. And this is called also affine Grassmannian. But you can just think of it as just a set of all hyperplanes in RD, because Grassmannian means some topological structure, additional topological structures. So a hyperplane H in this set, ADD-1, can be represented as a set of all points X in RD such that scalar product of X and some vector W is equal to tau for some unit vector W, this is a sphere in d-dimensional space. Unit sphere is in d-dimensional space, or we also denote it by what? By this. It's the same. And tau is a real number. So of course, every hyperplane has two representations of this form, corresponding to omega tau and minus omega minus tau, right? So if we want this representation to be unique, we must consider only tau positive or positive or non-negative and omega arbitrary omega, right? Let me assume that this hyperplane doesn't pass through the origin. So not passing through the origin. So origin. Okay, and now what is Poisson hyperplane process? Poisson hyperplane process. Hyperplanes process is a countable collection of hyperplanes such that if we take a representation of this hi in this form with omega I tau I, then omega I IID uniform on SD, and more precisely, if I take this distribution to be uniform, this will be an isotropic Poisson hyperplane tessellations. In general, we can take arbitrary distribution on a d-dimensional sphere, but we will consider only isotropic, which means that all directions are equally possible. These are IID. Tau I are also independent of these directions, and tau I form a Poisson process of unit and intensity for homogeneous Poisson point process of a unit intensity on R. So this is just arrival epochs of a homogeneous rate one Poisson point process. Independently of this process, we take uniform sample on a sphere representing directions of our hyperplanes, and we obtain a countable collection of hyperplanes, right? So in D, for D equals 2, this is just some field of random field of.
But they should be more far and far from the origin. Is it correct?
Right. So they're not concentrating around the origin, yeah, because this tau E is a Poisson process of unit intensity, right? So there are only finite number of hyperplanes, say, intersecting a unit ball, for example, just because these distances form Poisson point process of unit intensity. So if you take any ball around the origin, there are only finitely many hyperplanes intersecting this ball. It's obvious. And zero cell, this is a unique polytope. It can be checked that it is a polytope containing the origin. So this is our ZD. So unique cell, say, unique cell of the disjoint. Okay, it's simply, just take a look on this picture and so you see what is Z of D. So this is a unique cell containing the origin of a disjoint tessellation of RD by this Poisson hyperplanes processes. Unique cell containing the origin.
But let me ask you, you choose the unit vector uniformly on the sphere.
Right.
And then why are you thinking that you will have this polygon around the origin with non-zero area? How we can prove that it exists, like you grow?
so as I mentioned, so ZD is a polytope, which was proved actually in this paper. But to be honest, I don't know. Proof, it's intuitive that it must be a polytope, but the proof is not that easy, I guess.
Sasha, so do I understand correct that tau I are moments of jumps of a Poisson process? With,
yes.
So the distance from origin to the first line has exponential distribution. The distance from origin to the second line has Erlang distribution with...
Yes, right. But what do you mean by first line? The closest one.
Yeah, the closest line, yes.
Right, yes.
So probably the distance from origin to the boundary of this polytope is great. So a ball with radius tau1 is inside this polytope. So that's why it is not empty.
Nice. Exactly. Very nice explanation. So the fact that it is has non-empty interior follows from this explanation which Andrei gave, but the explanation why is it a polytope probably is not that easy. Okay, can I continue?
Oh yeah, yes.
Okay. So and it turns out that this constant is exactly expected number of vertices of the zero cell for isotropic Poisson hyperplane tessellation. For the Poisson hyperplane tessellation. So, and actually this can be restated as a convergence of this form fd minus 1 of this ball hull. But you will see in a moment a small difficulty. So this converges as n goes to infinity to the number of vertices of ZD. And the problem is that here we have vertices and here we have faces of full dimension. So there's some kind of duality. There's some kind of duality in this result. So here naturally we want to have something like the number of d-dimensional faces of something rather than number of vertices of something. But this can be resolved. This problem can be resolved. To explain how to resolve this problem, let me recall the concept. How much time do I have? Okay, not
like 15 minutes. Yeah.
Concept of polar body, or polar set. So the definition is the following. So we have Euclidean space with a scalar product. And we have a set A in this space. So a polar set, denoted in this way, is defined as a number of, so it, strictly speaking, it must be defined as a subset of a dual space, but in finite dimensions, there is no need to do this. So this is set such that supremum for x in A, scalar product of x and y must be smaller or equal than 1. And this set is called polar set. And it is well known that if A is closed convex, and contains the origin, then there is a duality. So polar set to a polar set coincides with A. And also if A is a polytope, containing 0 in the interior, then A0 is also a polytope. Also a polytope. So a simple example, if you take on a plane a unit square, this is A, then the polar will be also a square, but this one. This is a dual polar to S. This is 0.10. And there is a duality. So this is also known from the geometry that d minus 1, probably up to d minus 1. F0 of a polar. So there is a duality between, there is a one-to-one correspondence between k-dimensional faces of A and d minus k-dimensional faces of a polar. So for example, there is a one-to-one correspondence between the number of edges, of vertices of A and the number of faces of full dimension of the polar set. And the same for for all other dimensions. So on this picture, you see every, say, vertex or every face of A corresponds to a vertex of the polar set and vice versa. And keeping this in mind, this can be equivalently restated as this, of a polar set of a zero cell. What is a polar set to a zero cell? This is a already known object for us. This is a convex hull of the Poisson process PD1 appearing in this model. So this kind of duality. It's very simple, but for some reason it has not been, we have not been able to find it in the literature up to the last year when this result was proved, just four or five lines in Kabluchko again and Teli. But this is very simple. So I will give you a proof. So ZD, this is an intersection of half spaces over all hyperplanes in the Poisson hyperplane process in this P, such that H contains origin. So see, this is a simple definition of a zero cell, right? This is an intersection of all half spaces containing the origin. So in our case, so for this plane, okay, for all planes, we take only half spaces containing the origin, take the intersection. And now, using properties of polar sets, it is known that polar of an intersection is a convex hull of the union of polars. So this is a convex hull, to be more precise, with topological closure of this polar sets of this form. And polar set to a hyperplane, this is just a segment. This is just a segment. This is just a segment of this form. And since we know that this is this process has only finite number of atoms, there is only finite, actually no, only finite number of summands here, so closure can be removed, and this is a convex hull of PD1. Okay, now let me explain what type of convergence to random object we have behind this. Okay, so for me now I will denote by KD. This will be the set of all compact sets, compact convex sets in RD. And I put here 0 if I want the set to contain origin in the interior, containing origin in the interior, containing in the interior. In particular, this means that compact convex set should have an empty interior, so should be a body in the interior. Okay, X plus L is a translate. So this is by definition the set of all X plus Y where Y in L. L check or minus L, this is a symmetric set. So this is a set of minus X such that X in L. And DL is topological boundary. And I will also use notation K plus L. So this is so-called Minkowski sum of two sets. And also Minkowski difference of two sets. So these are all X such that the translate of L by X is contained in K. So this is Minkowski difference. Or equivalently, this is intersection of Y plus K for Y in minus L. Now, similarly to this definition of a ball hull, I will now define a ball hull with respect to a convex body K. So BHK of a set S is defined as an intersection of the all translates of K such that the translate contains S. So it's the same as here, but now we replace a ball with an arbitrary compact convex body, let's say, body. And we define the ball hull with respect to this set. And let me mention that if K is origin symmetric, so if K is equal to minus K, then this is the same concept as ball hull, but in Minkowski space. What does it mean? This means that K can be considered as a ball, but not in Euclidean space, but in some non-Euclidean space, right? With a norm defined by Minkowski functional, by the Minkowski functional. So with this remark, you see the connection between this concept of ball hull with respect to K and the ball hull, but in the non-Euclidean space. Okay, one more definition and then actually the main result. CN stands for centers. So in this definition of ball hull, right, we take all translates and the set of this X's such that translate contains S is called the centers. So on this picture, CN of B1 to 0, this is the set of centers such that translate of a ball contains this sample. So if sample is large, so you have points somewhere here, right? So the set of centers is a small set around the origin. So very just as, so in order to translate to contain a sample, you can only translate by a very small number. So this is a set of centers. And formally, this is defined as set of all x's such that k plus x contains s. So far, S is not a sample, is not a uniform sample. This is just an arbitrary subset of K. Okay, and in terms of Minkowski difference, this is just K minus A. Okay, and now let me take, as in a role of the set S, a sample of the U1, U2, and so on, UN. This is an independent sample of uniformly distributed points in K, uniformly distributed points in K. And let me define a random set Xn by definition as a minus set of centers with respect to K of this set S. So this is my Xn. So as the size of a sample tends to infinity, Xn becomes a small set always containing the origin. Yes, because S is a subset of K, so X is always here, but possibly also some small vectors X are also there. And now the main result, which gives, in view of this representation, so this is just K minus S from this, reads as follows. So this is my theorem. If you multiply Xn by n, so you scale this small set while multiplying by n, this converges in a Hausdorff distance to a zero cell of a Poisson hyperplane tensillation, but not isotropic, but with this distribution of omega of W1 being some distribution. With this distribution can be defined via the surface area of the body K. So here, this is a Poisson zero cell of Poisson hyperplane tessellation with distribution of W1 being the surface area, normalized surface area of K. So this is a normalized surface area of K. So it's self-explaining what it is, right? So you take an arbitrary subset of a unit sphere, right? So you take rays from the origin passing through this small set. These rays intersect K. Yeah, so there is some set of points of intersections of this rays with K, and the surface measure of this set gives you, properly normalized, gives you the distribution of W1. So in particular, if K is ball, this is an isotropic hyperplane tessellation. So this is the first part of the result, and the second part, for a polar object, this converges to the convex hull of the PD1. And short explanation of this, just 1 minute explanation of this. So what is this? What is this object? n-1, xn 0. So this is n-1. So this is n minus 1, and here we have intersection of k minus u j, j from 1 to n, and we need to take a polar to this. So this is just xn. This is my xn, the set of centers. And by taking polar, we know that this is convex hull of the union of polars. Ug, g from 1 to n. And now if we consider psi of n, so n can be put here inside. Now we take psi n. This is a sample of this form, n minus 1, k minus u1, polar, n minus 1, k minus put u2, polar, and so on, n minus 1, k minus un, polar. And this is a point process on the space of compact convex bodies. Point process on a space of bodies. And this process converges in the wake topology on this point process of space of bodies to the Poisson point process. Of this form. So this is a countable collection of segments where endpoints are points of the process PG1. And then taking convex hull gives you this result. And this result is obtained by passing to polar sets. And this is an explanation. Of course, after some additional efforts, you can show that F vectors are continuous with respect to convergence with Hausdorff distance after appropriate definition of this of the k-dimensional faces, and you can prove this convergence for all moments. Okay, I will stop here because I don't have time anymore. Thank you for your attention.
Thank you very much for such interesting talk. Maybe somebody have questions? Alexander, I have the following question. You consider as an original object, you consider convex, in some sense, convex hulls of uniformly distributed point in some area. And it is evident that this convex hull converge to all areas, for example, to all semisphere or to all unit disk in the second model. From this point of view, why it is interesting to consider such characteristics like number of vertices or so on? It seems to me that much more interesting is the characteristic of the polar set. For example, you considered this Poissonian tessellation organized from hyperplanes. It seems to me it can be used to calculate some mixed Minkowski volume of some sets and so on. So maybe there are some other functionals which also are interesting to study in this models.
Yeah, of course. So, for example, continuity of intrinsic volumes with respect to convergence of Hausdorff distance, it's well known. So, from these two results, you immediately obtain convergence of intrinsic volumes. So, it's not a problem. So, the main contribution here is not convergence of F vectors, say, like here. This was a motivation. So, this result was proved first, and then the question was what lies behind this convergence, and the answer is convergence. This non-trivial convergences to this.
Yes, and this is exactly my point. That originally you even consider the conversion of the polar sets, and maybe it is interesting to consider functionals from the polar sets. Related to the functionals which can be defined using this Poissonian tessellation. From other sets, you can see, for example, some other set in the space using Poissonian tessellation, you can just discuss the mixing volume of this set, just discussing the areas of the intersections of these hyperplanes with this set. So this can be a kind of functional which is interesting to see.
Oh, okay, I see. So you mean that a kind of functional convergence, right? And the functional convergence in the sense that we take as an argument an arbitrary set and intersect with this set.
Exactly, yeah.
Yes, so I believe this. I didn't think about it so far, but I think this is doable, and this is a proper way to think of this as to generalize this to a functional convergence, right? So to consider intersections with all possible non-empty, compact, non-empty bodies, compact bodies. Yeah, but
thank you. Maybe other questions?
Do I have 1 minute for a final remark?
Oh, yes, surely.
So this came to my mind when I was preparing this talk. So going back to this definition. So we have, again, manifold. We have finite, say, smooth manifold. Such that, so we have a uniform distribution on this manifold. We have an underlying group, either rotation or translation, or translations. And we define a generalized convex or generalized hull of a sample in this way. And the question is, so if we now consider, for example, in this model, a set G of n, so these are all rotations, such that G of SD plus contain our sample. So this is a non-empty set, non-empty subset of our group SOD containing the identity. So actually this is some neighborhood of identity. And our second model, the result of our second model says that, so in the second model, we can identify groups with RD, translate with RD, and we have convergence of this neighborhood containing the identity to a zero cell. So I strongly believe there must be some general theory. So if you take arbitrary continuous group, yeah, we take manifold, we take uniform distribution on this manifold. So we have some set of form Gn, which is a neighborhood of identity, and this set, as a subset of a group, must converge somewhere. This is what I strongly believe, but I don't have any rigorous results with this respect. And I would like to consider this problem. Looks very interesting. This is my remark.
Yes, it looks like you are right, but in my opinion, it is good to start at least from the not any continuous group, but with a group which has additional structure, like Lie group, or even group with Harmer, some compact group. Yeah.
Yeah, so far I would be very happy to have a general result for some, at least some general type of group. So just not just rotations or translations, but for as good group as you can imagine. Even for this kind of group, I would be happy to understand what is the underlying phenomenon for these two models.
Yeah, it is interesting. Okay, other questions, comments? If there are no questions, then thank you again. And now we finish our work for today. See you after a week. Bye.
Thank you. Bye-bye.
Thank you for nice talk.
Yeah, thank you.